Good afternoon, friends. Okay, so in today's class, we are going to learn how to obtain the stiffness matrix in reference coordinate system. The matrix in our previous class for the axially loaded members, you can see here, for the axially loaded bar, the stiffness matrix, which is given, which is called as the bar in the local coordinate system, which lies within the axis of the member, the axis within the member, where we have obtained the force and deformation relation with the stiffness matrix K. But this K stiffness matrix is in the local coordinate system. Now, in many instances, you have seen the bar elements are also called as truss elements, actually loaded members or stringers, and they are the members of the truss. But these members are not oriented with a straight line, straight axis, but it may be oriented in some other axis. So in many instances, we are required to conveniently write our stiffness matrix in both the coordinate system, that is local coordinate system and global coordinate systems. So we have to introduce the local and reference coordinate system in this case. As I mentioned, local coordinate system represents the member's individual axis. Suppose member is oriented with some theta oriented. So let us define the member's individual oriented axis is x bar and y bar. This is local coordinate axis. Now define the reference coordinate axis on the other hand, which is representing for the entire overall structure, and for entire truss we are required to convert our stiffness matrix in the overall, that is the global reference coordinate system, and that is x and y. And it is easy to handle the boundary conditions, applied loads in best possible manner when you formulate your problem, write your stiffness equations in reference coordinate system. So referring to this figure, we have already defined the x and y, which are reference coordinate system. X bar and y bar are your local coordinate systems. Now about the forces. You have seen that in truss members, it can only have the axial forces. So this is the joint 1 and this is the joint 2 that this truss is having, member of the truss is having, and it is oriented in counterclockwise direction from the x-axis, that is reference axis, in theta direction. Now these two nodes are having, of course, the axial force, that is x bar, x1 bar and x2 bars. These are the forces in the local coordinate system. Now when you resolve these forces in to the reference coordinate system, depending on the orientation, it will have two components of the forces, that is x2 and y2, because this force is likely to be resolved in global coordinate system, reference coordinate system, in two components. Now you may be wondering, because it is an axially loaded member, within the axis, that is local axis, there will not be y bar component. For example, here there will not be y bar. But when you orient and when you try to resolve this local force into global axis, there will be two components, that is x2 as well as y2 here. So there will not be y1 bar as well as y2 bar, but there will definitely y2 x2, and there will definitely here y1 and x1 component. Now how do you write these components? So you can see here that at each of the node we are having two force components required to be resolved into the reference coordinate axis. Those are x1 y1, x2 y2. These are the forces into the reference coordinate system. This y1 and y2 bar, x1 and x2 bar are coming from the resolution of the force components which are acting in the local coordinate system. The notations we have used, those are x1 bar and x2 bar. So these two components, actually the x1 bar and x2 bar will have the resolution of the force components, but in reference coordinate system it becomes the 4, and in local coordinate system the force components are 2. So we are required to, we have used the notation for the local coordinate system as bar over the symbols, and if now I am having 4 components of the forces at each of the node, I am likely to be write my stiffness matrix in local coordinate system also for the size of global coordinate system, that is 4 by 4. And how do we write? Okay, similar to forces, there will be a displacement and displacement components as well. When displacements in local coordinate systems are given by this u1 bar and u2 bar, you have actually u1 v1 u2 v2 in reference coordinate system, the corresponding forces to the corresponding displacement components. So we are required to expand this matrix to the size of the reference coordinate system, and we will write this K matrix, basically K bar matrix, which is in the global coordinate system, local coordinate system. We will introduce this matrix, which is expanded to the size of reference coordinate system. However, because y1 bar and y2 bar does not exist in the local coordinate system, also v1 bar and v2 bar may not be exist within the local coordinate system, we will try to introduce zeros over second rows and second column and fourth rows and fourth column. You may see here the components which are added in the second row and second column, fourth row and fourth column, these components are 0. Rest of the components are as it is, which is given in the local coordinate system. So we have simply expanded just by introducing the notations, which will help us in getting the forces in the reference coordinate system, as well as the displacement components and as well as the rotations. So this matrix, which is still in the local coordinate system, but it has the components which are corresponding forces required for the reference coordinate system. In short, we can write this matrix as x bar is equal to k bar u, small u bar. In short notation, you can write in the bold form. These are the notations. Okay, now how do we write the resolution of the components? As from the vector mechanics and vector algebra of the force resolution, simple definition of the from the engineering mechanics, we can easily write this component as x2 cos theta. It is a combination of plus y2 sin theta. So this component x2 bar can be written as one component of x2 cos theta of this vector, another component of this vector, that is plus y2 sine theta. So you may see here the components. Similarly, y2 bar can be written. This is just a representation of node 2 and whatever free body diagram of node 2 and whatever forces are there in local and global coordinate system. This is in global coordinate system. This is in global. This is in local. This is in local coordinate systems with the orientation is shown here. This is a free body point which is node 2. So we may write x2 bar is a combination of these two. Similarly, we can write y2 bar. So you can see here the left side are the forces in the local coordinates, whereas right side are the forces in the reference coordinate system. So we are able to somehow relate these two. This relationship is required, and you will be able to see that finally we get our transformation matrix from this. So let us write y2 is a combination of actually y2 cos theta and also the minus this force, that is minus x2 in this direction, the sine component of this can be resolved here. That is y2 bar is a combination of minus x2 sine theta plus y2 cos theta. Let us define lambda is cos theta, mu is sine theta. And similar operations holds at node 1. Instead of x2 bar, we will write x1 bar. Instead of x2, we will write x1. Instead of y2, we will write y1. Instead of y2 bar, we will write y1 bar. Instead of minus x2, we will write minus x1. Instead of y2, we will write y1. And finally, we write the forces on the left side, which is in, you may see this slide, that forces on the left side, you may see here local coordinate system, and the forces on the right hand side are reference. So those forces which relates with the local and the reference coordinate system with some matrix. Only thing is here we get 4 algebraic equation which we will be able to convert it into the matrix form. We can write in a matrix form and we get this relationship between these, but we get the matrix which relates with these two different forces, and we call it this as T matrix, that is the transformation matrix. And in the short notation, we can write x bar is equal to Tx, where T is your transformation matrix. X bar is your forces in the local coordinate system, force vector, and x is a force vector in the reference, which comprises of several members. Those are 4 members here, and this size of this matrix is 4 by 4, size of this matrix is 4 by 1, size of this matrix is 4 by 1. From this we may get x on the left hand side, then T inverse x bar. So T inverse is, if you invert this matrix, you get reference coordinate system forces on the left side. But it happened to see that if you inverse this matrix, it happened to be the transpose matrix and inverse matrix are same in this particular case. So we are writing T dash, this you can check it yourself, that your inversion as well as transpose matrix are same. So we have written T dash, which is the transpose of T matrix, and x bar matrix, which is the forces in the global local coordinate system. Similar relations holds for displacement components as well, that you can relate the displacement components in the local coordinate system with the transformation matrix, because they will also orient in the similar manner as the forces. So you can use the same transformation matrix even for the nodal displacement components. So you may see here, this is the local coordinate system displacements and this is a global coordinate system displacement, and this transformation matrix remain same as we have related with the forces. Okay, now how to obtain the K matrix in the global coordinate system? By simple algebraic manipulation. stiffness matrix in the reference coordinate system. We have this equation, we have already established that stiffness equation, the equation which I am referring again here, this is the equation. I am just writing in the matrix notation x bar is equal to k bar u bar. So you can see here x bar is equal to k bar u bar. This is the stiffness matrix in the local coordinate system. However, due to the relation of local and global coordinate system with the transformation matrix, you may see here x bar is equal to tx from, and also u bar is equal to tu. So from equation 2, we can substitute into equation 1 the relation which is x bar is equal to tx. So the left hand side x bar which is being replaced with tx. So you may see here tx. And the right hand side k bar remain as it is, and u bar, that is the right hand side, is also replaced by this equation, that is u bar is equal to tu. When you substitute here you get this relation. Okay, now we can bring this T matrix invert on the right hand side. Then we get x equal to T inverse k bar T u. So T inverse is nothing but T transpose. So T transpose k bar T u. Now what is this? On the left hand side we have forces in the reference coordinate system. On the right hand side we have the force displacement in the reference coordinate system. So finally we are able to relate forces stiffness equation in the global coordinate system with this relation. So what is this inside this stiffness equation? T transpose k bar T is what? We get x equal to ku. So what is this k? K is your T transpose. This is your k. It is T transpose k bar T, and this is stiffness matrix in the global reference coordinate system. So by substituting, by doing matrix operation, k bar is already there here with us. This is your k bar. This is your transformation matrix. So if you take the transpose of this, multiply that 4 by 4 matrix with this matrix, and also resultant matrix will be 4 by 4. Again, that matrix, if you multiply again with T matrix, you actually get the final matrix by matrix operation, because all size of the stiffness matrix, this matrix is 4 by 4, 4 by 4, 4 by 4. And when you multiply first these two matrix and then this matrix, you get finally the stiffness matrix in reference coordinate system. K is equal to AE by L, and these are the members. These are the terms we are getting, and again it is 4 by 4. Where lambda is of course cos theta and mu is your sin theta. So this is the matrix which can be calculated for any oriented members, but this is still a member stiffness matrix, member applicable to individual members. So when we solve the Truss examples for individual members, this matrix is required to be calculated for all the members, and then through our assembly procedure, which we have learned in spring assembly and bar assembly, the similar operation of the matrix assembly is to be performed to get the total stiffness matrix for the entire truss. So here in this case theta, when you make theta is equal to 0, you get actually k is equal to k bar. So you can change theta to get this element stiffness matrix. Please understand this is still element stiffness matrix for the individual truss member, but it is oriented in any direction. So you calculate the stiffness matrix in the global coordinates for any orientation. In our next class, we will try to solve one example for the truss. However, in your homework, you are supposed to verify this 4 by 4 matrix by doing this operation of multiplication T bar T dash K bar into T.